Hey guys, in this video I'm going to go over how to do Horn's parallel analysis, mostly in R. And before we get to the R demo, I just wanted to give a quick background of what you're doing when you're doing parallel analysis. So what the R code is doing. So parallel analysis is used for determining the number of principal components if you do principal component analysis, or if you do exploratory factor analysis, it can tell you the number of factors to keep. So if you're doing PCA, it'll tell you the number of principal components to keep, and if you're doing EFA, it'll tell you the number of factors to keep. And here's the basic steps for what Horn's parallel analysis is doing. So when you have a data set where you collect data for a certain number of samples and you have a certain number of items or variables, let's say that you have p variables in your data set. Any data set with p variables will automatically have p eigenvalues by definition of what eigenvalues are. Then, if you want to know how many of those eigenvalues do I want to keep or which ones are significant, you can do parallel analysis where you generate random data sets from an identity correlation matrix. And so basically you have an identity matrix has only ones on the main diagonal and zeros on the off diagonals. So when you generate this parallel data, what you're assuming is that the variables from this random data will be uncorrelated. And that means that if you generate PCA or EFA from this data, you're expecting that you'll have one principal component and zero factors from this randomly simulated data. So you're going to simulate this data multiple times and keep getting eigenvalues from this random simulated data. And your decision rule is going to be this third step here. So for any eigenvalues, so you have 1 through p eigenvalues, and these will decrease in the size of the eigenvalue, so the eigenvalue will get smaller as you go on if you order it from largest to smallest. If you want to decide whether to keep or retain your eigenvalue or to fail to retain it, you're going to look at the kth, whichever kth value that you have, and you're going to compare that to the mean of the kth eigenvalue from your parallel data. And if the kth value for your eigenvalue from your sample data is greater than the mean, then you retain that factor or that principal component. But if the simulated data that's supposed to be 0 factors or 1 principal component is greater than your kth factor or kth eigenvalue, then you're going to fail to retain that eigenvalue or that factor. All right, so that's kind of a brief overview of what parallel analysis is. So now let me go over to the R demo. Alright, so this is my R code to run parallel analysis in R. It's very simple. It's literally just one line of code that you have to run that will tell you how many factors or how many principal components to keep. And this function paran stands obviously for parallel analysis, and you have to install the package paran to run this function. So I already installed the package on my computer, and the first line of code just loads in the package called paran. And the second line of code just imports my data, and I've already done that. So if you run that, this will load in sample data that I actually simulated. So I simulated 1,000 observations of 9 variables. And the way I simulated the data, it should show me in the end that this is simulated factor data. So I simulated this 9 items that should show 3 underlying factors for this data. So when I run parallel analysis, I'm expecting it to show me that I will retain 3 factors because I simulated this data, so I know what the underlying truth is of the model. And so this is the line of code that you run to run parallel analysis using the paran package. So you just input your data first, and then for this line you have to determine whether it's true or false based on whether you're running exploratory factor analysis or principal components. So like I explained before, if you do parallel analysis for principal components, you're expecting to find 1 principal component. But if you run it for exploratory factor analysis, you're expecting to find 0 factors for the parallel data. So if you're running EFA, you want to have CFA is equal to true. But if you're running this parallel analysis for PCA, then you want to say false. So since I'm running simulated EFA data, I'm going to leave it as CFA is equal to true. So this function will print out your results in the console window, and you can also have a graph that looks at that I'll show you because I'm going to run it. It will show you the eigenvalues that are considered significant for the simulated random data and then for your sample data. So I'm going to leave graph as true, and then I'm just saying basically that when you graph it, I want it to be in different colors. And also, before I run that, if you want to know more information about parallel analysis, if you do $paran, this will open up some information from the package about this particular function. And I think this is really good R documentation. I think it has a lot more information than most R functions, I think. So if you're curious about any of the optional parameters for the function or a little bit more about parallel analysis, it has a lot of good information. And so the default for paran also is to compare the means. So like I said, it compares the kth eigenvalue to the mean of the parallel eigenvalue data. So another common way of doing parallel analysis is to use percentiles instead of the mean. So it's really common to do 95th percentile compared to the eigenvalues instead of the mean of the eigenvalues. So you can also do that using this centile parameter, but I'm not going to do that in this example. So finally, let's go ahead and run the function. So when the function runs, because I said graph is equal to true, it's going to print this plot. So if I look at this plot, the blue line based on my code is for the sample parallel data. So this is the random eigenvalues that are generated from the parallel analysis. And then you have adjusted and unadjusted from your eigenvalues from your sample data. We want to look at the adjusted because the adjusted adjusts for finite samples, which you'll probably have for your sample data. It's unlikely that it's going to be infinite. So we want to compare basically the black line to the blue line, and you want to keep as many principal components or factors that are above the blue line. So if you see here, you have 1, 2, 3 eigenvalues that are significantly above the blue line. And then when you get to the fourth eigenvalue, the sample data is below the generated mean of the eigenvalues for the parallel data. So you don't want to retain your fourth eigenvalue. And so that's how you would analyze it visually looking at the plot. And the paran function will also print out and spell out the results of the parallel analysis for you in the console. So it will tell you in the last line to keep 3 factors for your exploratory factor analysis. So I think those are all the main points that I wanted to discuss in this video. And also, before I end the video, this past week, specifically October 24th, I hit 1,000 subscribers on this YouTube channel. So I know that's not a lot of subscribers, but to me it's a lot. So I'm very excited about that. And for some reason the YouTube algorithm is like being really nice to me lately. So I've been getting like a lot of subscribers, more than I usually do. So I'm very happy about that. And thank you to everyone for watching my videos. And shout out to you if you're subscribed to me.